Okay, continuing on with colligative properties now, let's look at osmosis. Now, osmosis is the movement of solvent molecules through a semi-permeable membrane from an area of lower concentration of solute to higher solute concentration. The movement of the solvent, and only the solvent goes through the semi-permeable membrane, the movement of the solvent is to try to dilute the more concentrated solutions, to try to make the more concentrated solute solution be less concentrated. Okay, so let's set up a situation here where we have a container, and here's our container right here, and let's put in a semi-permeable membrane. It's like could be a piece of plastic. There's many biological semi-permeable membranes, such as cell walls, but it'll allow water through and nothing else. So let's semi-permeable membrane is right here, set to allow water through, and let's fill the left side up with water up to this level here, but let's only put this much on the right side, less water on the right side. What we see here, and what you can imagine, is the water on the left side, where there's more water, a taller column of water, has more pressure down here, and that pressure is going to push the water from the left side to the right side. And if you give it enough time, you will find that in our container with the semi-permeable membrane, the level of both sides of pure water is the same. Note that water is still moving back and forth between the semi-permeable membranes. This is a membrane, or back and forth between the two sides through that membrane. This is dynamic equilibrium. Water is going from the left side to the right side, but at the same rate, at the same speed, water is going from the right side to the left side. Okay, and that's probably not terribly new or unique, and that is not osmosis. This is osmosis. What if we take the same container with the same semi-permeable membrane that only allows water through? On the left side, let's put 1 molar sodium chloride. So this solution is a 1 molar aqueous sodium chloride solution, and this is a pure water solution. Note that the levels are the same. They have the same amount of liquid on each side. What we're going to find, if we give it some time, that some of the pure water is going to go over to this side. We're going to find that the left side, which had the sodium chloride, osmosis is going to try to dilute that. It's going to try to take some of the water from the pure water side and move it over to the sodium chloride side. Note, the semi-permeable membrane does not allow sodium chloride through, only water through, so none of the sodium chloride can go over to the other side. But osmosis wants to dilute this solution. Since this is pure water, concentration of sodium chloride 0, this is the left side is much more concentrated, so osmosis wants water to go over to the left side to dilute it. And that's what we'll find if you wait a certain amount of time, that the left side that has a solution will get larger in volume. The right side with pure water, the volume will go down. And this is a colligative property, which means it doesn't depend on the what's dissolved, just a number of particles that are dissolved. Recall, when sodium chloride dissolves in water, it dissolves into Na plus Cl minus. So Na solid, you put it in water, goes to Na plus Cl minus, which means our sodium chloride is, when it's dissolved in water, is 2 particles, the sodium cation, the chloride anion. What would happen, though, if we ran the same experiment here, but instead of sodium chloride, let's put in magnesium chloride in here? Well, when we put in magnesium chloride, MgCl2 solid, it dissolves in water, but note, it will dissolve into 1 Mg2 plus 2 Cl minuses. Note, it's very important, remembering from Gen Chem 1, how to break up ions when you're doing reactions. When ionic compounds dissociate, you have to remember that yes, the 2 goes in front of the Cl, which means we have the 2 Cl minuses plus the magnesium. We have 3 particles. What this means is 1 molar magnesium chloride is actually 3 molar in terms of particles. There are 3 moles of particles per 1 molar magnesium chloride. 1 mole of magnesium chloride breaks up into 3 particles. Therefore, 1 molar magnesium chloride is 3 molar in particles. 1 molar sodium chloride is 2 molar in particles. And I forgot the chlorine here. Not a problem. Just fix it like that. All right. So 1 molar sodium chloride is 2 molar in particles. 1 molar magnesium chloride is 3 molar in particles. Colligative properties only depend on the number of particles, which means this solution down here is more concentrated in particles than this solution. The magnesium chloride solution is more concentrated in terms of particles than the sodium chloride solution, which means if it's more concentrated when we have the magnesium chloride solution, what we're going to find, the level of the water, level of the solution of the magnesium solution is going to go up even higher than the sodium chloride solution. The pure water level on the right side will be much lower, well, even lower than the sodium chloride solution, because this was a much more concentrated solution to start with. Therefore, more water has to go in there to try to dilute that. And because this is all based off of pressure, you really have the pressure of the gravity is providing pressure of the water down here. And you also have the osmosis trying to get the water from the right side to the left side. Not all of the water on the right side, the pure water, will go into the left side because the pressure is building up due to the height of this column of water here. But the force that is causing the pure water to go over to the other side to dilute that solution, we call that force the osmotic pressure. And yay, there's a nice equation for osmotic pressure. Capital Pi, osmotic pressure, equals the concentration of the solution times R times T. Note, concentration of solution is molarity, moles per liter. R is the gas constant, 0.0821 liter atmosphere per mole Kelvin, temperatures in Kelvin. And when we look at this, this is pi is osmotic pressure, which is pressure. Concentration is moles per liter. R is a gas constant. T is temperature. Note, if we multiply both sides by liters, which is a volume, liters is a unit of volume, so really this is just pressure times the volume equals moles times the gas constant times T. This is the ideal gas law. This osmotic pressure equation, pi equals CRT, is just another way of looking at PV equals nRT, only the pressure is osmotic pressure, and we tend to look at the concentration of our solute. All right, cool. Moving on. Here's an interesting thing that you can do when you study colligative properties. You can determine the molar mass of something just by examining its colligative properties, especially boiling point elevation. And you could use freezing point depression also. So, and truthfully, you could use osmotic pressure, osmosis also. So let's look at this. Our setup, how are we going to think through these problems? Here's our basic thinking. We're going to look at a colligative property such as boiling point elevation, freezing point depression, osmosis, something that changes the vapor pressure of our system. Now, from the equations, that can give us our concentration of the solution. If we know how many degrees the boiling point is lowered, and if we know the constant, that gives us concentration. So if we know concentration, we can use the mass of the solvent to get the molarity of the solution. And once we have molarity solution, if we measured grams of our original solute, we can calculate the molar mass. That sounds a little concentrated. You're probably saying, what? I'm not following. Well, let's go through an example here. All right. Say you have a solution that you made from 1.25 grams of oil of wintergreen, methyl salicylate, also kind of a spearmint type flavor. So you have this oil of wintergreen, you put 1.25 grams of it in 99.0 grams of benzene. We did not use water here because wintergreen does not dissolve in water very well, but it dissolves in benzene very nicely, so we had to choose a proper solvent to dissolve it in. So we've got our 1.25 grams of wintergreen, 99 grams of benzene, and we find that this mixture has a boiling point of 80.31 degrees Celsius. Question, what is the molar mass of methyl salicylate? What is the molar mass of this oil of wintergreen? How many, what's the molar mass, grams per mole, the molecular weight? Well, note, we have our equation for boiling point elevation. The change in the temperature of the boiling point equals as constant times the molality of the solute. Well, check it out. Doing the little math, since we remember from a few videos ago that benzene has a boiling point, a normal boiling point, pure benzene is 80.10 degrees Celsius. That tells us we have a 0.21 degree temperature change for our boiling point elevation. So delta T boiling point is 0.21 degrees Celsius. K, our constant, boiling point elevation constant, is something you look up in a table. And so that's 2.35 degrees Celsius for molal. So then we can now calculate the molality of our solution here. It is 0.083 moles of solute per kilogram of solvent. All right. So, note, if we have 0.083 moles of solute per kilograms of solvent, our molality, we had 99.0 grams of benzene, which is 0.099 kilograms. Kilograms cancel, and that says we've got 0.0082 moles of our solute. So just by looking at our boiling point elevation, so far we can calculate the number of moles of oil of wintergreen, 0.082 moles. But no, we weighed that out. We weighed out 1.25 grams of oil of wintergreen. We didn't know it at the time, but that 1.25 grams of oil of wintergreen was 0.0082 moles of oil of wintergreen. Our change in boiling point gave us that information. But then we also know that the molar mass is grams per mole. So take the grams of oil of wintergreen, 1.25, divided by the moles that we got from our math here, and that gives us a molar mass of 150 grams per mole. And 150 to 2 sig figs, because we've got a 2 sig fig number right here. Note that the actual mass is 152.10, which is 150 to 2 sig figs. So that's pretty cool. If you can find something like, what is this stuff? Well, I'm not sure what it is. Well, what's its molar mass? I don't know. Dissolve it in a solvent, or weigh it out first, dissolve it in a solvent, see how it changes the boiling point, and then through math you can figure out the molar mass of that thing. All right. This video is going to go a little bit long because I want to finish up this. Well, actually, let's stop this video here. It is 13 minutes. We need to look at some other issues involving these colligative properties and then move on to colloids.